Thank you. Thank you all. Thanks for attending. It's great to be. It's a pity I can't be in Australia with you. I would really have liked to, but it's nevertheless great to be able to give this online conference. So what I wanted to talk about is a particular aspect of Scala III, probably the biggest thing we've redesigned, and that's implicits. Implicits is probably sort of one of the biggest defining features of Scala. A little bit, it wasn't planned that way. I will talk more about that, but it came to be that way over time. And while we did that, there were a few sort of forks in the roads and stumbling blocks and rocks over which we fell. And I'm also going to tell you about those. So the talk is Implicits Revisited. And I want to start by saying, well, implicits in Scala are really everywhere. And we have proof for that. There's a paper at UPSLA 2019, which has analyzed 7,280 Scala projects, 80 million lines of code, 8 million and implicit call sites were found, and 370,000 implicit declarations. So 98% of all projects, Scala projects, use implicits, 78% define implicits, and 27% of call sites are implicit calls, which is quite a lot. So it's really one of the most heavily used features of Scala. They're everywhere, but it's fair to say they're also probably the most controversial feature of Scala because, well, a lot of people got bloody noses using them. They are competing designs that are also very elegant, like Haskell's type classes that some people prefer. And so implicit sort of had to find a place in the world. And what I want to do is look a little bit back in time and essentially tell you how implicits came to be about, how essentially implicits were discovered, because that was more or less what it was. We stumbled on them, and also some of the mistakes we made. So that's sort of me being on a rock, glancing out in the distance in the mountains, and said, oh my God, if only I could turn back time and do things better. But maybe with Scala 3 we have a chance now. So this talk covers how implicits became what they are today, some design decisions that turned out to be mistakes, and also where I really want to essentially emphasize some design decisions that turned out to be right in the end, and a redesign in Scala 3. So the history of implicits were actually the first step towards implicits were implicit conversions, which is kind of ironic because implicit conversions now are considered to be the most problematic feature of implicits, but they were the first. So in 2004, the first Scala version ships with implicit conversions. Why is that? Why add such a powerful feature? So the motivation was that essentially I was sort of puzzling for a long time over the late extension problem, which was like a big problem at the time. I was talking to Guy Steele about that, who also was working on that. So what is the late extension problem? The late extension problem is that if you have a class and a trait or interface, how can we make the class extends the trait after the fact? So essentially you can change neither the code of the class nor the interface. How can you make the class extend the trait? Well, essentially nowadays we say type classes, but at the time we were firmly in an object-oriented setting, so this was a really hard problem. And the so-called solution that we eventually came up with after discarding many other possibilities and going into dead ends was implicit conversions, that we say we cannot extend the class C after the fact. Also the fact that we were on the JVM, we had really hard limitations in what magic we could pull with the native codes. So bytecodes were a very, very harsh format. So we cannot extend C after the fact, but we can create an automatic wrapper. And that's very powerful and essentially solves the late extension problem to some degree. But the downside is it's also easy to misuse. But hey, at the time, Scala had maybe 5 users or something like that. So it wasn't deemed a problem at the time that it was easy to misuse. So that's how conversions came about. And then 2 years later, implicit parameters were introduced, and that was sort of more or less because it was easy. because once we had the basics of implicit resolution, that means that if you need to find something that's implicit, essentially, how do you go about it and find it? Where do you search? And all these rules. It's tempting to, once you have those rules, to also do something to have implicit parameters with it. The delta is relatively small, and the expressive power would include type classes, some version of type classes. So I want to take you back in time to a talk I gave in 2006 at the IFIB Working Group of Functional Programming in Boston. And those were the original slides with some of my annotations of today. So the title of the talk was Poor Man's Type Classes. That was what essentially implicits were labeled then, or that was my term for them. So the goals are, type classes are nice. A cottage industry of Haskell programmers has sprung up around them. Can we add type classes to OO languages, specifically Scala? So OO languages, triple exclamation mark. At the time, Scala was firmly an OO language. It was an OO language with functional features, and it sort of morphed into sort of a fusion that essentially is more stands on both legs, and more as we progress, we emphasize the functional parts. The problem with at the time is that the problem with that is the conceptual expense. We have a bit tongue-in-cheek already spent the keywords type and class, so type class is out. And also you can observe that type classes are essentially implicitly passed dictionaries, and dictionaries are essentially objects, and we don't want to duplicate that. So we concentrated just on the delta between OO classes and type classes, and that led us to implicits. So then I essentially introduced the implicit parameters. That was like the very first example, where you see here the implicit parameter of a monoid, and here it gets inserted by the compiler. So the red code is the code that the compiler inserts here. So we can combine normal implicit parameters. However, there may be only one implicit parameter list, and it must come last. That's also a restriction that has proved to be annoying over the time, and that we will remove in Scala 3. So then it goes on and says implicit can also be used as a modifier for definitions, like for the string monoid and monoid objects there. And then there's the canonical list example where you pass the int monoid implicitly. Okay, and then comes the fine print. So how are implicit resolved? So we say, okay, an argument for an implicit parameter of type T, if it's missing, it's inferred, and an argument value is eligible to be passed if it's labeled implicit, its type is compatible with the parameter type, and now it comes one of the following holds. X is accessible at the point of call by a simple identifier. That is, it's defined in the same scope, inherited or imported, or it's defined as a static value in some superclass of T, so a member of the companion object. If several arguments are eligible, choose a most specific one, and if no most specific eligible argument exists, type error. So what's striking with this definition is that it's really very, very simple. So I could put it on one slide, and it's perfectly nice. It was actually optimized for being simple, and that has proved to be a problem because essentially this one phrase that captures it all, that it says contextual implicits as just those implicits that are accessible at the point of call by a simple identifier, that has turned out to cause a lot of problems, and we'll see what problems it did cause. Okay, and then the other thing is, then I go and talk about coherence or locality. So a consequence of implicit argument resolution is that one can have several instance definitions of the same operations at the same type, and we always pick the one which is visible at the point of call, if there's a unique one. And that's an important difference, which was acknowledged at the time, between implicits and type classes. So the rules to keep coherence, which is essentially the local coherence, that means basically unambiguity. The important rule here is that in Scala, we distinguish between functions, which are objects, function values, and methods, which are not objects. And partially applied object methods are automatically converted to functions by a process called eta expansion. And we say only methods but not functions can contain implicit parameters. So that means implicit parameters are instantiated where a method value is eliminated, either applied or converted to a function. And that has actually turned out to be also more or less by accident the biggest win of implicits, because that's the one thing where implicit parameters in Scala are different from implicit parameters in Haskell. And implicit parameters in Haskell are actually quite unpredictable, and to no small reasons, because they don't follow exactly the same principle. They do something for polymorphic values and another thing for monomorphic ones, and it's very hard to essentially figure out when these implicit parameters in Haskell are instantiated. And that's, I believe, also why nobody uses them in Haskell, or very few people use them. Okay, then it goes on and it gives the standard examples about conditional implicits. So you can have list monoids if you have monoids over the elements, and here's the code, and here's the instantiation, which is, of course, a recursive instantiation of implicit instances parameterized by other implicit instances. Okay, so in retrospect, going forward to today, what did we get right? So I think what we did get right, and what we will continue to do, is the following points: that type classes are types, nothing else, not essentially as another thing that lives outside the type worlds. Dictionaries are just values, no magic about them. Instances can be defined anywhere. Local instances are possible. No global coherence requirement, and the relationship with eta expansion that I mentioned before, that implicits are passed in the expanding context, which actually makes them, in my experience, extremely robust from that perspective. That you say when essentially what implicit value does flow into this thing, it's very predictable because of that rule. Okay, so what were the mistakes? So I believe the mistake number one was depending on the names. So there was this clause that I repeat, one of the following holds: X is accessible at the point of call by a simple identifier. It is defined in the same scope, inherited or imported. Very simple rule to express, but very confusing consequences. So what are the consequences? Well, the first one is that names matter where they shouldn't, and shadowing is a problem. So here is an example. You have an implicit value, A, and then you have a function that happens to be a parameter of the same value, and then you can't find the type TC as an implicit anymore because you have something called shadowing. So that means that, well, it does find the TC here, the implicit search finds it, but then there's actually a special check that says, well, could I refer to this value A just by its simple name where I am? And the answer is no, because the simple name would actually refer to the parameter and not to the implicit. So that implicit fails. And that's a pity, because essentially the implicits are implicits. Because implicits are implicit, the names shouldn't matter, but here they do. The second mistake related to this, I believe, is that nesting did not matter. So this one gives an ambiguity. If you have an implicit val A of a type class and a function that takes an implicit evidence of the same type class, and you call implicitly of the type class, then you get an ambiguity, because now you have two names in scope, the A and the EV, and they both are of type TC. So you have to be very careful to actually always use the same name. And that's sort of an extraneous requirement, which is, from a user point of view, a little bit bizarre. So that was, I believe, mistake number two. And mistake number two also means that coherence is a real problem. So there was a paper by Adabel Chang and some others on essentially why coherence is a problem in Scala, also from a point of expressiveness, so not just from a point of essentially uniform and safety. So the example they gave were essentially you had a function f, which had a type parameter f that was both a monad and a traverse. And monad and traverse are two type classes that both extend functor, and functor has a map instance. And then you want to call map from this function f. So the question is, should you get the map instance from monad, or should you get it from traverse? Of course, you say, well, it doesn't matter. They both got the map instance from functor, and it's hopefully the same. But without a global coherence argument, the compiler cannot be sure. So maybe jumping through a lot of hoops, we could get there. But right now, the answer is no. It cannot be sure. So that's ambiguous, and that's very annoying, because it means you have to essentially pass explicit dictionaries at some points and you have passed more and more of them, the more complex your type class hierarchy gets. So the obvious fix for that would be to say, hey, let me just disambiguate it. Let's just say here locally, my functor should be the monad. It doesn't matter, dear compiler. It's monad and traverse have the same functor instance, but that's only I as a programmer know that. You as a compiler don't know that. So let me tell you. Let me just say you assume the functor is the monad. And in current Scala, that doesn't work, because it's even more ambiguous than the previous one, because now we have essentially this local functor and the monad here and the traverse over there, and they all compete for the implicit value, because nesting does not matter. If nesting would matter, of course, the functor would take precedence and the problem would be solved. Okay, the mistake number 3, I think, is less serious, but still annoying, is I believe we have similar syntax for quite different concepts, and that's very confusing. So in particular, implicit conversions and implicit instances look just so alike. So here, the first one, that's an implicit conversion called A, and the second one, that's a conditional implicit. So if you say implicit conversions should be avoided, and I agree to that, and on the other hand, conditional implicits are everywhere, then it's very confusing that the two look so much alike. And for essentially newcomers and casual users, it's very hard to keep them apart. And I think the fourth mistake is that implicit parameters are too close to normal ones. And that was also basically the reason. The reason for that was that initially we took a shortcut. We didn't want to introduce more complexity from the outset. So the shortcut was that we said, well, if we have an implicit parameter and you want to pass it explicitly, which you should be able to, then you just write a normal application. Right. So, but that leads you into problems in cases like this, where you have a function and the function takes an implicit parameter EV and it returns a function value. And you would just want to apply it. You want to pass the implicit value implicitly, as they are supposed to do. And you want to apply f to some value of type u. You can't write f of u right now, because that gives you a type error, because it mistakes the u for the implicit parameter. And it says, well, that's not the right type. What you can write is f.apply u, because now you have made it clear to the compiler that f is really what you really want is the function value f, which you want to apply to the u. And then the compiler says, oh, I have to pass the implicit value and to get to the function value, and there you go. So that means that implicitness is a leaky abstraction. It really shows. Normally, if things are implicit, you should never be worried about essentially that they might get into your normal application flow and things like that. But here they do. And the reason for that is, again, to essentially to say, well, initially, we didn't want to add too many complications in there. So we want to pair implicit parameters with just regular calls. We didn't want to invent a separate syntax for those calls. So I think that was a mistake as well. So taken together, implicit started as a way to express conversions, and we generalized the mechanism to provide type classes, extension methods, and many other kinds of contextual information. The mechanism is impressively flexible and powerful. So compared to, let's say, a more direct type class approach, the difference is really here we expose the mechanism, and that gives you more power because the mechanism can do other things than you defined on the high level. On the other hand, the mechanism often tends to hide the intent and the overall architecture of what you do. So that's a problem with it. Okay, so now I come to Scala III. It's a major redesign of the language. It's built on researched foundations, namely DOT, which is the dependent object calculus, and its emphasis is on making it easier to use and making it safer to use. The first stable release will come out later this year. There's a research prototype DOTI that's been elaborated over almost 7 years now, the last 7 years, and DOTI is morphing into Scala, which you see with this logo here. So on the top you have DOTI, and it's sort of flowing into Scala, and hopefully we will be done by the end of this year. So one of the biggest changes in Scala 3 is revisiting implicits with essentially, in hindsight, with everything we'd learned, that essentially what we didn't realize at the time is how important they would become. Initially, Scala didn't have them. Once it had them in more restricted form, and now essentially they are everywhere. So it's time to essentially rethink them from the ground up. And if you rethink them from the ground up, then I think that the core concept really is term inference. So we know type inference. So Scala is a language that does type inference. And implicit search is really analogous to that. Only now the compiler infers a term. From what does it, or an expression, I should say. Term is sort of expert lingo for expressions or values. So what does the compiler use to infer a term? Well, it uses the type. So I say, I want a type, I want an implicit value of a certain type. I want to summon that value. And the compiler produces the canonical term for that. So we trade types for terms. We give the compiler the type and we get back the term. So the idea now is that instead of adding, implicit as a modifier to many different constructs and tweaking the meaning of each in slightly different ways, we want to have a single construct to introduce a designated term or expression that can be inferred for a type. So we want to bundle it all in one concept and say, okay, there should be a syntactic construct that says, if you want to infer the term for that type, then essentially, here's how you define a candidate term for doing that. And we call these candidate terms implicit given instances or just givens. So here's an introductory example, pretty much standard one for ordering. So let's say we have a trait ordered of t, and it has a compare method, and it has less than and greater methods. And then we have an implicit instance int ord, which is an ordered of int, and it redefines the compared method, which was missing up there. And then we have a conditional implicit instance list ord of t that uses the fact that t must be ordered to prove that list of t is ordered. So that's how you write it. Given list ord of t, using ord, that's an implicit parameter of type ord of t as ord of list of t, and then you define the compare. So what's different is we don't say this is a function or an object or whatever. We just say, well, this is how you essentially synthesize the given instance for this type, and we want to abstract intentionally a little bit on what exactly will come out here. It suffices to say, well, there will be some form of values that essentially will have the necessary methods, but how you get those values, I mean, you can figure it out. There's a guide what gets produced, but it shouldn't be your primary concern. Your primary concern should be essentially what are essentially the types that are instances of a type class that is represented by a trait. Okay. So this was still a little bit verbose, but as I said before, for implicits, the names don't really matter, so we can leave them out. So we can also have a given instance where we just say given ord of int, so int is ordered, and here's the compare method, and we can say given ord of list of t, where t is ordered. That's just a good old context bound that we had before as well, and here's the compare method. So that's essentially how would you would usually write that, and if you write that, the compiler will just synthesize names for the givens here, which usually don't matter because you don't really need to reference them explicitly. Okay, so those correspond to essentially, if you look at what you did before, essentially given objects and given classes with creator methods and things like that. But given instances can also be aliases. So that you can see by just the equal here. So we can say, well, for instance, here, given, let's name it global as an execution context equals a fork join pool. So that means now you have an implicit called global of type execution context instantiated to be a fork join pool. Or they can be anonymous. For instance, you could say in this scope, the given position should be the position of the enclosing tree. or they could be actually quite complex as well. So for instance, here we say the given context, assuming that an outer context, outer is the outer context with a new owner called current owner, something like that. Okay, and the last part of it is now we've seen how to define these given instances. How do we use them? So there's also a difference now. So instead of implicit, we write using. For essentially using means that a function uses an implicit term instantiated inferred for a type. So the max function uses the fact that T must be ordered, and the evidence for that fact is called ord. That's the parameter, and essentially it has the usual implementation. So implicit parameters are passed in using clauses, and they can be anonymous. So I could also write using ord of T if I don't need to refer to the parameter directly, for instance, because all I need to do with the parameter is pass it on as an implicit to further methods. Then I could just write using ord of T, which is the normal case. So again, I can leave out the name. These parameters then, of course, they are inferred as usual. So I can just write max 2, 3 or max of list of 1, 2, 3, nil, for instance. And but I can pass them as well. And if I pass them, then the argument syntax has to mirror the parameter syntax. So I have to use using as well, which solves this abstraction leakage problem I referred to earlier, that essentially normal calls are confused with explicit arguments. So here, that's no longer the case. If you want to pass an ordering to the max function, you have to write using again. And of course, you can do that recursively. So you can also pass an int ord to a list ord if you want. Whereas you cannot do this anymore, so you can't just write max 2, 3 int ord, because that there it would say, well, the maximum function doesn't take more further parameters, because all it does take is implicit parameters in using clauses, and you can't pass user normal parameter clause for that. Okay, so let's see how it would work for type classes. So here's a simple example, the standard one with semigroup and monoid. So it really works actually quite well out of the box with extension methods. Here's how you would write semigroup of T. You would say, well, we have an infix method combine, which works on an X, on the left-hand side, and a Y on the right-hand side, and returns a T. And then we have a monoid, which is a semigroup, and it has a unit method. And then we have a monoid instance of string, where we say our combine method is just string concat. Sorry, that's a stray open parent. That was a typo. And then we have the unit method is just the empty string. That's another typo. Sorry, I fixed those late last night. So then the sum method then would look like this. It would just say fold left over the list of excess of list T, where T's are monoids, and we say summon monoid of T of unit. So we get essentially the monoid instance, and we get unit with a little bit more boilerplate and auxiliary definitions. I could make that nicer, but now with the raw code, all I had, I need the explicit summon here, and then use combine as the combining function. So what's missing here is essentially all the jumping through hoops to get infix syntax for type classes, which currently is a big problem. That's why packages like Simulacrum exist, and that's all gone away because essentially type classes and extension methods integrate very well with each other. What you need in particular is that an extension method can be abstract, like you see in the example here, so it can actually be part of a type class which is represented by a trait. Okay, so we've seen summon. So summon is the new implicitly. So it can be defined quite simply like this. So summon uses an implicit parameter of type T, and it returns the parameter itself. Its type is a little bit better than the type of implicitly. The return type of implicitly would be T in this case, whereas the return type of summon is really x.type, which matters sometimes when you work with path-dependent types. You have a better type for the thing you're searching here. I believe summon is exactly what in shapeless would be called the. So that's the way to summon implicit value in shapeless. Finally, let me get to conversions. Implicit conversions with implicit defs would be no longer supported. Basically, all uses of implicits will be dropped. Instead of that, we will have a conversion type class, which has instances like this. So conversion is defined in the Scala package, and you can have, for instance, to convert a string to a token, you would write there's a given conversion from string to token where the apply method takes a string into token and essentially wraps the string in a keyword wrapper. Or you can use an alias given that's makes it shorter, where you say that my given conversion of string to token is just the keyword wrapper. So that just uses same types for mapping the lambda into the conversion. Okay, those conversions are yeah. Okay, let me just go on in the interest of time. So there are also many polishings. So I showed you mostly the surface and the syntax, how you express things, but there are lots of improvements in details. So given instances and parameters can all be anonymous. We've seen that. Nesting is significant. Shadowing is eliminated. So the previous problems that I mentioned are restricted. We have a more robust prioritization of implicits, which means you don't need to go back to essentially these elaborate class or trait hierarchies where low priority implicits go into super traits. So there are other ways to do that now. There are a lot. The error messages have improved quite a bit, and I believe the most important thing is that if an implicit is missing, now the compiler gives you an import suggestion. So it will essentially look on everything you have on the class path, and it will say, well, you might want to import this implicit or this given over here, and that will might solve the problem. And that essentially I found gets me unstuck a lot of time when I work with code I don't know, and I got the same feedback from other people. So for the migration, the current implicits are still supported in Scala 3. They will probably be deprecated from Scala 3.1 on. So they have to be supported in Scala 3 because Scala 3 is expressively wants to support cross-building between 2 and 3. So it should be binary compatible. So we will share the same standard library and the same binary artifacts, and it should be possible to cross-build libraries and applications between 2 and 3. So that's why basically everything that we have in 2, or most things we have in 2, are still supported in 3. Only things where it really was too awkward to do that. But in the future, they will probably be deprecated. So if I would write a book on Scala 3 or teaching materials on Scala 3, I would not mention the word implicit anymore. Because they will be gone a while later. There are some special provisions for cross-compilation. The most important one is that the given arguments also work for old-style implicits. So that means I can use a using clause even when I call into an old-style method that takes an implicit parameter and not a using clause. Can I yet take a using argument? And that's important because that means I can first convert the users of libraries to the new version, using everywhere. And then I can bring over the library safely and map implicit parameters to using clauses and without breaking all the user code. Okay, so try it out. It's at .epfl.ch. We still have 5 minutes left, or 5 to 10 minutes left. So I just want to go quickly into another thing that might be have been on your mind if you paid attention. And is the topic of optional braces, which is also something that's new in Scala 3. So you might have noticed that our Scala code got a lot slimmer. Curly braces and parentheses are now optional in many more places, and they're generally left out. And instead of braces, one can use indented blocks. And that has caused a lot of angst and outrage in people. So I want to sort of explain a little bit what's going on and what you can expect. So the fact is that there's actually a lot of code variation today in Scala. So here you have some arbitrary Scala code, and some write it like this. They put the braces here. Some others including lately when I was using braces, I really disliked the else behind the closing brace, because essentially the else should be something that introduces a new section. It shouldn't hide behind a brace. So I wrote it like this, spending an extra line. Okay, so you can do that. Some people also leave out the braces if there's a simple statement, because then the braces are really useless. They're just essentially noise. The problem with that is that once you add another statement, then you have to remember to put the braces back in, or you will get surprises in the compiler error messages. And of course, there's no real uniformity in where you put the parents and things like that. So some people like to write the parents immediately after the if. Some people write a space and so on. So that's my point is there's a lot of syntax variation today, and people don't get upset about it. They said that's okay. We can have a formatter that uses our favorite style, but we acknowledge the different styles. And what we also allow now is that we say, well, you can leave out the braces, you can leave them in, or you can leave them out, or even better, you can also leave out the parents if you follow this thing with a then. So you can write it like this. And other uses of what we allow now is for a for, so you don't need the braces around here, and for a while, for a match, for a try. So all these things can be written without braces, just with what we call quiet syntax. So optional braces, like what I've shown you, are very controversial. So we added it first as an experimental feature, and I've now used it heavily for more than half of a year. Yeah, I think almost 9 months, I guess. And I must say the experience has been positive for me beyond what I ever expected. For me, it's actually the single most important way how Scala 3 improved my productivity and also my joy of coding. It's just so liberating not to have to do these braces anymore. My slogan here is indentation is really like Lego bricks, and braces are like baling wires. So indentation, you just put things where they should go at the proper place, and that's it. You just plug them together, and you don't need to think about more further than that. Whereas with braces, it's sort of like you put this one thing here, and it's okay, and then you put a second thing here, and now I have to wrap this whole thing because otherwise it will fall apart. And this wrapping thing is essentially like a baling wire of a bunch of hay or something like that. And braces look like that already, so they really are like that. So anyway, so there's also measurable improvements. Programs become shorter. On average, I observed more than 10% reduction in line count because you don't have these endless things of essentially closing braces anymore. And for writing, it's ideal because writers stay in the flow. You don't need to go back and forth inserting braces, which is, for me, I think, hugely disruptive. There were, before I did that, a lot of people coming out and saying, oh, this will be terrible for refactorings. It doesn't scale. It doesn't work in a large setting. And I observed absolutely none of that. There were no downsides. Program changes were a lot more reliable than with braces. Of course, the details matter. So details in the language matter. Essentially, how do you make sure, for instance, how do you do the meta rules in the language that is essentially if you accidentally insert or delete a single space that the program will not essentially change meaning. So we have essentially this meta property in the rules for essentially our insignificant indentation. So these things are important. Tooling is important. I'm using an editor that has essentially these light gray lines, vertical lines on the tab stops. So that's absolutely helps a lot because essentially that's your analog of jumping back and forth with braces to find out what's a region. But once these things are in place, I think it really works great. Okay, so that was essentially this final thing, and I think I'm at the end of the talk. Thank you.